Okay, so I just finished. Hopefully the lighting is better. Sorry, some of the videos are going to be dark, some might be light. Deal with it. So when last we met, we were talking about the one-dimensional particle in a box. My notes take you through determining the wave function, testing the boundary conditions. Again, we're bound to that box. And then the notes also explain how you would go about validating whether or not that wave function, after it's normalized, satisfies the Schrodinger equation. So please look at those. They will help you out. Now, how do we translate this to 3 dimensions? Well, it's through separation of variables. So if I have a particle stuck in a box with x, y, and z, so those are the boundaries that are going to affect its motion, then I can say that my total wave function is going to be totally lost words. Separation of variables. So you've got 3 independent functions, one f of x, one g of y, and one h of z. And the nice thing about the separation of variables is you can actually take the Hamiltonian. Again, we don't have a potential energy, so you just have the Hamiltonian with the kinetic energy operator operating on f of x, so d dx squared. Operating on f of x gives you my energy in the x direction. The same thing gives you the energy in the y direction, and then the same thing gives you the energy in the z direction. So you can take the Hamiltonian, operate on psi of x, and just get f of x, g of x, and or g of y, and h of z. So that separation of variables keeps them all independent in the different directions. And the result is that the total energy, you'll have an x component, a y component, and a z component. And so pretty soon what we're going to do is we're going to be looking at degeneracy. So you can have 3 energy states that all have the same energy. However, they will be unique. And that uniqueness comes from one might be an energy in the x, one might be an energy in the y, and one might be an energy in the z, but they're all 3 the same value. So that's where degeneracy really originates. Okay, so the information that we gather from the wave function for n equals 1, again, this is that quantum number associated with the energies of a particle confined to a one-dimensional box, or in this case, 3 dimensions. So if n equals 1, this is going to be the shape of our wave function. And if n equals 2, you have a shape like this, n equals 3, and so on and so forth. Everywhere we have something, the wave function crossing the 0 point, we call that a node. Now remember, you're also 0 at the boundary. So that's just the wave function plotted. If you want to look at the probability distribution, you have to look at psi squared. And psi squared is going to give you these types of shapes. And the thing I want you to keep in mind is as you get to infinitely high energy states, that's where, imagine if it looks something like this. So this is just an infinite number of these bumps, if you will, whereas essentially what you have is a continuum here. And so now this is called the Bohr correspondence principle. Niels Bohr, who we will be reading next Friday, chapters 1 through 4. The Bohr correspondence principle says if you go up to a high enough energy state, you've essentially reached classical physics. And that's exactly what we have done, because now there is no longer a higher probability here and a lower probability here of finding our particle. Now you have a continuous probability of finding the particle, such that you open the box, you look down, and you have an equal probability of finding that ball anywhere in that box. Okay. Any questions? Look at the notes, because I can't help you.